Welcome to the future.
Welcome to the Muxall Open IoT channel. I am your host, Michael Crane. In today's extended video, we continue our investigation of the I2C SDA and SCL waveforms from our ESP32 to our NHD-C LCD that's using the ST7528i I2C Controller. We look at spikes in our SDA waveform, which we believe to be AC coupling effects. At least that's what the internet said. We also investigate a Runt pulse by decoding an I2C command captured on our oscilloscope. Could it be our I2C ACK from the Sitronix? We're going to find out. We use the oscilloscope also to measure the rise time of our SCL pulse and do a little mathematics to calculate the I2C SCL bus capacitance. Then we compare our numbers with the Sitronix datasheet, and based on our calculations, we choose different I2C pull-up resistors so we can change our rise time. We finish with some I2C speed tests at 100 kHz and 400 kHz and take a final look at our improved I2C waveform. So let's get started. Okay, so we are able to ping our LCD over our I2C. If you'll notice, the waveform here looks much better. Now, I have to admit, I did make a change to the pull-up resistors. I replaced them from a 5K to a 2.4K, and then I was reading on the internet that because this is chip-on glass, it might not be able to pull down a 2.4K resistor, and they suggested a 10K pull-up resistor for the I2C. Now I'm talking about the I2C pull-up resistors. Okay, and you can see it looks okay. You see these little glitches. Let me see if I can zoom into this real quick. So you see these little spikes right on the top of that. By the way, the bottom one is the data, the top one's the clock. You see this little spike right here on the top of the data line, and you notice how it kind of lines up with the clock. Okay, so it's been a couple days. Actually, it's been almost a week since I was looking at this waveform. And so I pulled it back up, and as you can see below here, I have a speed test on there to see how fast we can write digits to this. Because as you know, if the user's trying to turn a knob, right, you don't want the update to be really slow. As you'll see, when it's displaying the Muxall logo, see right now, that's basically at 100 kilohertz writing basically the whole display. It's about 10,000 pixels or something like that. And so you can't update the whole display, so I had to write some code to update part of the display. And that's what it's doing now, is it's just writing numbers, and it's still at 100 kilohertz. Before we get off what I was talking about before, about these little spikes right here. Let's see if we can look at them. What I was reading on the internet, these spikes are caused by AC coupling. And what's interesting on the previous one, if you remember, when the data line, so it's clock on the top, data on the bottom, when the data line dropped, it was also having an AC coupling effect on the clock line, but I'm not seeing that anymore. I'm not exactly sure why. I haven't changed anything. Maybe it has something to do with probing. But one of the things I noticed when I was looking at this is we've got a little bit of a runt going on there, and it doesn't seem to be affecting how the display is working. But I thought we'd take a look at that real quick. Real quick back on this AC coupling. When the clock line drops, it's coupling to the data line, and it's giving the data line a little nudge down. right? And from the research I did online, there were people that said, well, you know, you need to move your traces apart a little bit. And that might be okay for the PCB, but the traces on the flat flex going to the LCD can't be moved apart, and they're very close together. So I think we're just going to have to live with it. It doesn't seem to be affecting anything. But this little runt pulse has got me kind of curious on what's causing that. I'll go ahead and run it, and I'll zoom out some. Okay, so starting a test. And you can see these just little runt pulses kind of all over. And I'm not exactly sure what's causing that. Hopefully that's not the the ACK. But I would think if it was the ACK not working, the LCD wouldn't be displaying properly. And that's what I was going to do. I was going to see if this was the end of our byte and this was like some kind of very bad ACK coming from the Sitronix LCD controller. Okay, I went ahead and captured some data and stopped it here. Yeah, let's go take a look at this guy right here. This looks like it might be a command. And that should only be about 3 bytes. That'll be easy for us to decode. So let's move over here. We'll zoom in. Oops. Okay. Yeah, it's... Well, if these are acknowledges, that's 1, 2, 3 bytes. Okay, it probably is a command. So let's see if we can decode this thing and see if that's what it is. I got my cursor going here. Here's the start condition. So the SDA drops, the data line drops at the when the clock is high. That signals a start condition. All right. Here's a transition period. Here's a data bit. So we got a 0. Okay. I'm going to write this down. So we got a 0. Okay. And oops. We transition. Now we got a 1. So we've got a bunch of 1s. So it's, let's see, there's 1, 2, 3, 4, 5, 6. So we got 6 1s. 2, 3, 4, 5, 6. There's what we got so far. All right. This is the start. Here's the 0, and there's the 6 1s. All right. Now we've got a 0. All right. Now it looks like we have 2 zeros. All right. We got a 0, and we've got our runt. Okay. Hopefully you can see that okay. What do we got here? Then we've got our runt pulse. And we've got a transition. And we've got a 1. So, yeah, I'm guessing this is the transition for the runt. This is the bit for the runt, which would, the acknowledge. So we're going to call it 0. And it's going to transition back up. And then we got a 1. Okay, that's kind of what I'm thinking it is. And then we're going to have more data bits, which looks like it's a 1 and a bunch of zeros. Not exactly sure what that is. It's a 1. Well, let's count them. So I'm thinking this is the acknowledge. It transitions, we get a 1. And then we get 1, 2, 3, 4, 5, 6, 7. Yeah, so we get a 1 and 7 zeros. That definitely sounds like a command. Then while I'm editing this, I'll I'll pull up what that command is on the and put it in the video so we can look at it. I don't know what it is right off the top of my head. It does sound like a command though, or it looks like a command. Yeah. So and that's then we get the acknowledge, right? So we got exactly 8 bits, and then we get our little runt pulse, which is the acknowledge. Okay, just reading the manual. It says that the device that acknowledges must pull down the SDA line during the acknowledge clock pulse, so that the SDA line is stable low during the high period of the acknowledge related clock pulse. A master receiver must signal an end of the data to the transmitter by not generating acknowledge in the last byte. Okay. I was reading the Sitronix description of an ACK, and it says each byte of 8 bits is followed by an acknowledge bit. The acknowledge bit is a high signal put on the bus by the transmitter, during which time the master generates extra clock pulse. Well, then I was reading this TI paper, and it says an acknowledge is actually a low bit. A NAC, a not acknowledge, is a high pulse. So I'm not exactly sure. I hate to disagree with the Sitronix people, but I believe this TI white paper is probably more accurate, at least from what I'm seeing on the scope. So it says before the receiver can send an ACK, so that's the Sitronix, the transmitter, which is our ESP32, has to release the SDA line. To send an ACK bit, the receiver shall pull down the SDA line during the low phase of the ACK-NAC clock period. That's what I keep calling the transition period. So that the SDA line is low during the high phase of the clock. Okay? And they're saying that an ACK is a low clock pulse. So if that's what we're seeing right here, if the transmitter, the ESP32, is releasing the SDA line at the almost the exact same time. I wonder if we can actually see that. At almost the exact, so if it's releasing the line at almost the exact same time the Sitronix LCD controller is trying to pull it low, that might be the reason why we're seeing this what looks like a runt pulse when it's actually 2 different devices making this pulse, right? So this part is okay. The ESP32 released it, and this part right here is a Sitronix grabbed it and yanked it back down, right? So everything's looking pretty good. The problem is right now is we're running at 100 kilohertz, and that's pretty slow. If you watch the logo paint on there, you can see it's pretty slow, even though these digits look pretty fast. Now this Sitronix will handle up to 400 kilohertz. So I'm going to go ahead and set it to 400 kilohertz, and we'll take a look at what the waveforms look like at 400 kilohertz, okay? Alrighty, I've changed the clock speed to 400 kilohertz for the I2C bus. And we capture a little bit of data. Let's see if it starts back up here a little bit. Oop. Yeah. Now we go. It doesn't look very, our square waves don't look very square anymore, do they? This AC coupling doesn't seem to have changed. I guess it's changed a little bit. Maybe it's a little more pronounced. But you can still see where now you can really see where our 10K resistors are causing us problems. I mean, this is probably barely in conformance. We'll have to look at the spec sheet, maybe do some calculations on that. Maybe with it, we could probably figure out what the capacitance is on the data and SCL lines. But the good news is, if we watch this, and we can time this, it's theoretically it should be 4 times faster, right? Let's see. It should start up here in a second. We're not quite running at 347 kilohertz. Well, I even cleared it. But man, that's a lot faster. So in case you're wondering, this is the paper I'm using to validate the I2C on our LCD bus, or for our LCD, right? This is the chip that is on the glass of our NHD-CD, okay, LCD, sorry. And if we go to page 23, I think it is, 24, it talks about the I2C interface, stop-start conditions, system configuration. Here's that acknowledge I was referring to earlier, and they've got a couple graphs. Very nice. Here's the format of the control bytes that I was showing, that we were looking at earlier. Here's the start condition. Here's our address, which we saw, and then they have this SA0, SA1, SA0, and then the read-write bit. I don't remember what these guys are, but okay, yeah. So the SA bits are the least significant bit of the slave address, and you can change it by connecting the input SA0 and SA1 to either logic 0 or logic 1. All right. But this is what we were interested in. So here's where I got the 400 kilohertz max clock frequency. And here's all our timings. But what we're interested in is capacitive load represented by each bus line. So the max it can handle is 400 puff, right? Okay, so I've got a little spreadsheet here I use for calculating the capacitance on the bus. This is the rise time. This is actually from the spec sheet, 300 nanoseconds max. And here's our pull-up resistor, okay? And this formula, you can look at it here. It's kind of unreadable there. Came from another TI data sheet. This guy right here, okay? And here's the equation. Oh, by the way, here's the name of it, I2C Bus Pull-Up Resistor Calculation. And by Rajan. Sorry, I hope I'm not destroying your name too bad. Anyway, page 2 here is calculate the how to calculate the pull-up resistor for the max pull-up resistance. They've got a minimum here. We're not really interested in that. We're interested in this maximum pull-up resistance because it's based on the rise time, and we want to try to reduce this a little bit to change our rise time, right? Because the only way to change the rise time is to change the pull-up resistor, right? But first, what we want to do is we want to see what the capacitance is on our bus, all right? Because we know we can measure the rise time. We know what our pull-up resistor is. It's 10K, right? So we want to see what the capacitance on our bus is right now, right? So let's go measure the rise time with a 10K pull-up resistor, all right? Okay, so we're going to need to calculate or measure the rise time. And this is at 400 kilohertz. The problem with that is I can get the cursor up very close to the start, but trying to figure out the end point of this right here is not going to be very accurate. So what I did is I went ahead and downspeeded the anyway, we can look at it real quick. So it's still at 400 kilohertz. So I got cursor A set, cursor B. See, it's like, is it here, which is showing about 1.4 microseconds, or yeah, I don't know. it'll be better on the 100 kilohertz, because at least it squares off at some point, right? So I'm going to go, it's already booted up in 100 kilohertz. I'm going to go ahead and run this. All right. And let's see here. I'll go ahead and stop this. Okay. So here's, I could make this a little bigger. So here's our start. All right. And, ooh. Cursor A. I'm going to put cursor A on our start. Cursor B. I'm going to put, it looks like about right there. Let's see, what do we have here? Oh, well, 1.3. So I guess it was close either way, which makes sense, right? They should be relatively close. I was just having, I was just not, this right here you can see is, it's squared off, right? We got on the start and it's kind of where it squares off. And so I'm comfortable 1.3. All right. Okay, so we got 1.3 microseconds. If you multiply 1.3 microseconds by 1,000, you'll get it nanoseconds, which is 1,300 nanoseconds, right? So we've got about 153 puff, our capacitance on our bus, right? Let's go look at that spec sheet again, if I can find it. All right. So, well, we're well outside the 300 nanosecond rise time for SDA and SCL lines. So, we didn't actually measure it on the SDA line, but it's going to be about the same, I'm guessing. The traces pretty much run parallel to each other. That's why we're getting all that AC coupling, right? Anyway, you're showing the 300 nanosecond rise time max and a bus capacitance of where is it? Here it is right here, 400 puff. Well, we're underneath that 400 puff, so that's good. But yeah, our rise time is that's pretty bad. So, and you're probably wondering why it's working, or you might already know. And the reason is by the time it gets to a certain point, right here in at some point, it calls it good, right? And from here to here is probably, within the 300 nanosecond rise time. And we could go on the oscilloscope and check it, but it doesn't matter. We know it works, so we can see it. So from here to here, we probably getting our our 300 nanosecond rise time, and then from here to here is the other 1,000 nanosecond rise time, right? And as long as it makes it to whatever point on the data bus where it calls it good, so if it goes 2/3 of the way up, and the chip says, the Sitronix chip says, "Oh, that's good enough. I've got a good signal or a clock," then the rest of it doesn't really matter, right? I hope that kind of makes sense. I'm probably not explaining that as well as other people might, but by the way, this picture is of the I2C running at 400 kilohertz, okay? Because this is what we want to try to smooth out, right? So we calculate that we have about 1.53 puff on our 153 puff on our capacitance on our bus. What we need to do now is figure out. Yeah, we need to move this around, this equation around, so we can solve. Because we know our capacitance is 153, we know our pull-up resistance, so we want to trim this back and see if we can get it in this this 300 nanosecond range, right? And that'll square this off better. I mean, we just need to get it close, because we know this works. I could probably leave it like this and it would be okay, but when we start adding more capacitance to it, it's just going to get worse. And we have to remember, when we add our button panel, it's going to add a lot more capacitance. Hopefully it won't double it, but that might be what we're going to use to calculate it, right? Like a worst case scenario. So if we pull up our calculation right here, it gives us TR equals 0.8473 times RP times CB. So that's easy enough. So we're going to say, here's TR, and this is going to be RP and CB. All right. And so this is going to equal 0.8473 times RP times B27 times C27. Right? Make sure that's right. 0.8473 times B27. Yep, and C27. Okay. Let's see here. So this is going to be in, well, we want this in puff, right? And puff, and this will be in, and we want the rise time in nanoseconds, right? Okay, so we need to not do anything with that. C27, we need to multiply it by times 0. And puff is what, 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Does that look right? It's very small, so now we need to multiply. We need to get this down into nanoseconds. Okay, and so we want to divide this guy. I think that's right. Divide them by 0.123456789. Oop, 1. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. Oh, 130 nanoseconds. Well, that doesn't seem to match. Oh, that's because our resistor is not 1,000 ohms, it's 10,000. Okay, there we go. That's more in line. Yeah, and if you're wondering why it's off, it's because of rounding errors in the computer. There's probably a way in Excel to make it not round off so much, but that's okay. We're close. We're looking at the big picture, right? We're just trying to get in the ballpark. Okay, now let's I want to do a quick sanity check. Make sure that the math is right here before we get too far along. Looking at the scope here, we know that our frequency is 347.2 kilohertz. So if we have a frequency of 347,200. All right. And then lambda, which is going to be 1 over the frequency. This equals 1 divided by this guy. All right. If we multiply this guy by 1,000, that should give us microseconds, right? So times, not 1,000, 1,000,000. 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 1, 2, 3, 1. Is that right? 1 million. So this should be in microseconds. All right. Okay, so half of this, so this is our wavelength, so half of this is going to be 144 microseconds, right? And I can just say just 1/2 of lambda just equals this divided by 2. All right, 144, this is in microseconds still. Okay. All right, so half of that is from this point here to this point here, right? So this is half the wavelength. All right, because then this would be the other half. So it goes. So this is the wave, right? You start here, come down, and it goes up. I know it's a little crooked. It's not. It's a little crooked. It's not a nice square wave, but anyway, you get the idea. Okay, so 144. Now that's it. Now this is in microseconds, and we're saying the time to rise is in puff, which is 1296 nanoseconds. So, you know, if we convert this 1/2 lambda to nanoseconds, which is basically just taking this and multiplying it by 1,000, right? Whoops. Equals this times 1,000. There we go. Okay. Now, does this make sense? So it's 1,440 nanoseconds long, and our rise time 1,296 nanoseconds. Yeah, that looks pretty close. So what's the delta? So delta. How about we do 1/2 lambda minus TR. So it's this minus this. So 144 nanoseconds, or 0.14 microseconds, is the how long it's holding it high. And let's look at our spec real quick. Where is that guy? Yeah, so we're at 0.14, and we should. So the minimum for the SCL clock high period is 0.6. So we didn't quite meet the spec, and we knew that. I mean, you can look at this, but you have to remember what we were talking about earlier is it only needs to go 2/3 of the way before it's going to call it a good pulse, or something like that. I looked in the spec; it actually doesn't say, or I couldn't find it. How much of this? It's usually in, or you know, VDD times 2/3 or something like that. But I couldn't find it in the spec, so we're just guessing. We know this works, so it's calling it good somewhere. We'll say 2/3 just as a rough estimate. Okay, so this all the math here seems to be matching what we're looking at on the screen of the scope. So let's go back to our calculation here, and we want to try to whittle this rise time down. We also want to do it with a higher bus capacitance, because as soon as we add our button panel, this is going to change. So we're going to add, I'm going to add another 150, approximately 150 puff for button panel capacitance. Okay, so that's going to make this 300, which is really close to the to the max that this Sitronix chip says it can handle. So yeah, this is going to probably cause problems, and we would probably find that if I plug the button panel in, our LCD might stop working. So we need to kind of look at this now. Okay, so what if we put a 5K in here? Okay. That brings us down to 1271 nanoseconds, and we're still way outside of the spec. You remember what was it before? So we're at 1296. We know this works. We double our bus capacitance, and this is a worst case, right? And then have our pull-up resistor to 5K. So what would we have to plug into this guy to bring it into spec? What if we plugged in 2.4K? Woo! Wow. That's still way outside. It's still two times out of spec. Yeah, and I wouldn't feel comfortable going any less. Yeah, see, there's no way we could put a 1.2K resistor on that because this Sitronix, this chip on glass won't pull it down, right? Yeah, and I don't remember if I showed you this earlier, but I'll show it to you again. It says, in chip-on-glass application where the track resistance from the SDA out pad to the system SDA line can be significant, potential divider is generated by the bus pull-up resistor and the ITO track resistance. And this ITO is something to do with the chip-on-glass conductor. I don't know what it is. You can Google it. I Googled it. I don't remember exactly, but I think it's like a paste or something. Anyway, it's not as good as a trace, and so it's got its own resistance, and it's going to cause a voltage divider with our pull-up resistor, right? And it says it is possible during the acknowledge cycle, which is that little spike we saw that we were looking at earlier, that it won't be able to create a valid zero level. In other words, it won't be able to pull it down far enough to to register a zero. And then it says you can split it out, but it says in chip and glass application, it's required is necessary to minimize track resistance. Yeah, so another thing we could do instead of dropping this resistor down, or where are we at? Dropping this resistor down is we can shorten the PCB trace. But yeah, that's probably going to be hard. And a lot of it's on that flat flex going to the LCD anyway, right? I don't know. Let's see, what was 5,000? Yeah, I mean, that gets us right back to where we are at 400 kilohertz. You saw it at 100 kilohertz, it was okay. So we need to plug in a 5K resistor and see if this thing's going to be able to pull it down for the acknowledge. Okay, so I went ahead and plugged a couple. They're actually 5.1K, so they're 5100 ohms. So we should be seeing but we're at 153 puff, not 300. So let's see here. We should be seeing a rise time of about 661 nanoseconds. Let's go to the scope and see if that's what we get. Okay, so I've got the controller board fired up. It's still at 100 kilohertz. The I2C bus is still at 100 kilohertz. And I've got the scope on it. So let's see what we got here. Let's see. All right, getting some data now. Let me zoom out a little bit. There we go. That looks like something good to look at. So I stopped it. Let's go ahead and zoom in. Okay, so that's one cursor. Let's see. Oh, we'll do cursor A right here, and we'll put cursor B. Whoa. That's not the cursor. Cursor B. Right there. And I'm just using my eyeballs. Maybe it'd be easier. Let me see if we can, blow it up a little bit more. Move it over a little bit. We can get a good look at it. Okay, so I'll put cursor A right at the beginning. Alright, cursor B. What do you think? About right? Right there. So about 700 nanoseconds or so. I don't know. It's hard to tell. I guess I could put another cursor up on this guy right here, and I think we're pretty close to our calculation. Would we say 661 is our calculation? And let's see, here's 660. So yeah, the math works, right? So well, that's good. At least we know our math is good. So yeah, let's zoom back out, and I'm going to go ahead and stop the camera. I'm going to reboot the board into 400 kilohertz mode, and let's see what it looks like. All right. So the board's booting up with the I2C bus set to 400 kilohertz. I'm going to go ahead and start the scope again. And when I say start, I mean I'm hitting the run button. I don't know if you can see it. Oh yeah, you might be able to. Okay, so we're getting something now. And well, it seems to be kind of all over the shop. Let me hit clear. So it's 250 kilohertz. Really? It looked like it was bouncing between 250 and 500. Let's let it run one more time here. Let me make sure I didn't fat finger something in. Yeah, no. Oh, here we go. So the average is, wow, it's just really jumping all over, isn't it? But okay, so our average is it looks like it's around 380, 375, 380, I guess. Okay, I think that's about what we were saying last time. I'll go ahead and stop this. Let's zoom in on one of these guys. Well, that looks much better. Just, oops. Yeah, it almost looks square now. So, yeah, there's no need to measure it. We know what the rise time is going to be. But yeah, we can see this definitely looks better. We need to go look at our ACK. I forgot to do that. And that's this guy right here, right? And move him over a little bit. Yeah, so it's, oops. This is, oh, here's our ACK right here. Oh, que pasa? Yeah, so here's our ACK. This is where it takes over. So we're getting a nice clean pull down on that. So yeah, gosh, we might even be able to increase that resistor size. It seems to be able to pull it down okay. Well, we'll do that. If I plug the button board in and, and we start having lots of problems, then I'll go ahead and change it. I don't really want to muck around with it too much because it seems to be working at 10K pull-up resistor and a 5.1K, and our clock looks better. It could be more square, I guess. I don't know. I didn't measure these this AC coupling. You know, having a faster pull-up on these guys is probably just going to make it couple even more, right? This is a curious little. Yeah, there's another one right here. I'm not sure what this is right here. Yeah, I don't know what that is. There's nothing else on the bus, and it doesn't seem, I was looking at some print statements on the console, it doesn't seem to correspond with anything else, so, but it seems to be everywhere, right? So I hit run again. But yeah, you can, that's just a little knee right there. I don't know, maybe it's, every time it's getting ready to ACK it, I don't know what that is. That is odd. Yeah, I was sitting there looking at this a little bit. Yeah, I can't figure out what that knee's for. I thought maybe it was a Sitronix doing it, but I do believe that one there is coming from ESP32. So I don't know, is something getting on the line trying to test, to see if the SDA line's been released or not? I don't know. If someone knows, maybe they can post a comment. That would be pretty interesting. But it doesn't seem to be affecting the operation of this, so I'm not going to worry about it too much, and I don't know if I could do anything to fix it. But yeah, if anyone knows what that is, if one of the chips is, that's how it's monitoring the line, as putting a little bit of a voltage on it before it takes over, let us know. It'd be very interesting to find out.
Don't forget, you can support the Muxall Open IoT channel by donation using a credit card and PayPal, or by purchasing products at the Muxall store. Details and links are in the description under this video. Well, that's it for this video. If you liked the video, give it a big thumbs up, that helps, and hit the subscribe button. That really helps. If you have any questions or comments, post them in the comments under this video. Thanks for watching, and I'll see you next time.